go to worked out examples. Problem 1. JFET in the circuit shown in figure has IDSS 10 milliamperes and VP minus 5. The value of resistance RS for a drain current of IDS 6.4 milliamperes. Select the nearest value. And the data is given here and the circuit is given here. So the basic idea is again three things: input KVL, output KVL, use the VI equation. So how much is the nearest value we need to calculate for RS? So far he gave the circuit and asked us to calculate the Q point. Now he is giving the Q point and asking for circuit. That's given in GATE EC 1992, 2 marks. This is JFET. ID is equal to IDSS into 1 minus VGS by VP whole square, and ID is given there, and it is IDS is 6.4 in 10 power minus 3, 1 plus VGS by 5, and that value is VGS by 5 is equal to this. And from input, VGS is equal to IDRS. If you substitute there, you will get RS value of 156. And when you get 156, it is approximate the nearest value is 150. Therefore, our option is A. Problem 2. For N-channel MOSFET and its transfer characteristic shown in figure, the threshold voltage is, look at here, it is starting from 1 volt. This VG is 3, VD is 5, and VGS is 1. And this is the transfer characteristics. So what is the threshold? This threshold voltage is 1 and the device is in active region. With threshold voltage is minus 1 and the device in saturation region. 1 volt when the device is in saturation region, and minus 1 volt and the device is in active region. This is given in GATE 2005 EC 2 marks here. Let's go to problem. If you look at here, from the clearly we can see that current is increasing, therefore VT is 1 volt. From input KVL, if you apply, VGS is equal to 3 minus 1, because 3 here, 1 here, what is the value existing here? 2 volts. And if you really apply here again, VDS is equal to 5 minus 1, it is 4. So VGS is 2, VDS is 5, and that's the characteristics we have. And hence, if you compare, VDS is greater than VGS minus VT, that is 4 is greater than VGS is 2, 2 minus 1 is 1, therefore 4 is greater than 1, therefore MOSFET is in saturation region. The condition for saturation is VDS is greater than VGS minus VT. That's the condition for us. Therefore, option is C there. So 1 volt, saturation region. Common data problems. For third and fourth problem, the circuit is given as a common data. A small RD is a means internal resistance is 20 kilo, IDS is 10 milli, VP is minus 8. So minus 2 here, 2 mega here, 2 kilo and 20. This is the values we have to calculate. What is the input impedance? What is the output impedance? Also, we may be asked here. And let us use this circuit to solve the next problems. The first problem on the circuit is calculate Zi and Z0 of the circuit respectively. Generally, Zi is internal impedance is infinity. Infinity parallel anything is same thing. Therefore, he gave 2 mega parallel infinity is 2 mega. Therefore, option is 2 mega. Then what happens to supply? DC supply will act as a short circuit. DC supply will as a short circuit, and that short circuit value is grounded. Therefore, it is infinity parallel 2 mega is 2 mega. Similarly, when you draw the AC equivalent for AC, all supplies are grounded. You know why supplies are grounded for AC? Supply means 20 volts. AC means change in 20 is 0, because in DC there is no change. No change is to say 0 volts. 0 volts means ground. That's why from now onwards, remember, the AC equivalent of DC is always 0. So let me calculate that. So it is 2 mega, and internal resistance also important because he gave small RD as 20 kilo. So 2 mega is correct. 20 kilo parallel 2 kilo ohms here. So 2 kilo parallel 20 kilo. How much comes is that? So this is given in gate 2005. So this seems to be 2 mega is okay. Then a small RD we have to cross check. Small output is equal to small RD parallel capital RD. 20 into 2k by 22. So 22 by 20 by, because if you cancel this, 11 will come, 20 by 11. So this is output impedance that you have. So you have in first questions done output impedance. Therefore, option is B. Option is B. Problem 4 is a link to the same question. It's a common data. Therefore, ID and VDS under DC conditions. Same year. Calculate these values. He gave ABCD's options here. We need to calculate. IDQ is equal to IDSS into 1 minus VGS by VP whole square. Standard equation and 5.625. And if you substitute, VD is equal to VDD minus VD IDRS, and that is 8.75. So 8.75, 5.62. If you see here, you got the answer and option as A. A is the option here. Problem 5. An N-channel depletion MOSFET having 2 points on its ID VGS curve. VGS is equal to 0, ID is 12, and VGS is minus infinity, Z0 is infinity. Which of the following Q point will give the highest transconductance gain for small signal? The whole idea is you have to get the expression of conductance and then substitute highest and lowest. So values of VGS is given to you and you need to solve it. And as you know, GM is equal to 2 IDSS by VP, 1 minus VGS by VP. 2 IDSS by VP, 1 minus VGS by VP. Therefore, option is D. Option is D. Problem number 6. For the N-channel enhancement MOSFET in the figure, the threshold voltage is equal to 2 volts. The drain current ID of the MOSFET is 4 milli. When the drain resistance is 1 kilo. If the value of RD is increased to 4 kilo, the drain current ID will become. The drain current ID will. You can see here it is options are given to you. It's gate EEE 2003 2 mega. So this is 10 minus ID RD, directly it goes to VGS. That's one equation you have. From that equation you can solve for ID. So let's go for 10 minus ID RD, just jump to VGS, and VGS will come to you as this. This is 10 minus 4 milliamperes into 1 kilo, it is 6 volts. So VGS value is 6, and if you substitute, ID is equal to K into VGS minus VT whole square, 6 minus 2 whole square, and you will get K as 1 by 4. Not only that, K is 1 by 4, and you can put that value back in this value. So VGS is 10 minus ID into 4K. What is ID? K into VGS minus VT whole square. What is K here? 1 by 4. 1 by 4 into 10 minus 4 ID minus 2. If you substitute these values and the Kirchhoff's laws from output KVL, you will get ID as 2.84, 1.4. And MOSFET should not be greater than V threshold. Therefore, ID is 1 milli, 1.4 milli. Option is C there. Problem 7. The value of R for which PMOS transistor in the figure will be biased in a linear region. The value of R for which the PMOS transistor in the figure will be biased in a linear region. So 4 volts VDS, threshold is 1 volt, 1 milliamperes, and then this value we have to calculate. This is also given for EEE students. And don't think EEE is not, electronics is not important for EEE. You can see the questions now, and let us see what is the option for this for. From the figure, what you can say is this 5, Vs is 4, Vgs 0, Vt is minus 1. Therefore, Vsg is equal to 4 directly, because you are coming here and jumping here, and that's nothing but gate. So when you go for output KVL, VDD minus VSD minus Vs is equal to, where VSD, the source to drain, is equal to Vs minus V. So 4 minus IR, because there is a resistor here, I into R. 4 minus IR. Now if you substitute in the linear region, 4 minus IR is less than or equal to VGS minus VP, and then you will get the value of R as 1000. So when you say 1000, greater than 1000, you can say answer is D. Problem number 8. Assume that the N-channel MOSFET shown in figure is ideal, and that is the threshold voltage is 1 volt. The voltage VAB between the nodes A and B is how much? That's a problem. We have to calculate voltage here, VAB. Options: 5 volts, 2 volts, 1 volt, 0 volts. Gate EEE 2005. Look at the equation here. Circuit diagram. This is equivalent because he said ideal. The figure, it is clearly observed that from the source voltage 2 volts, enhancement conduct heavily and act as a short circuit, because you are giving 2 is beyond 1. When you are giving beyond required, and it's acting as short circuit. Therefore, the voltage between VAB is equal to 0. Assume that the threshold voltage of N-channel MOSFET shown is 0.7 volts or 5 volts. Can also be shown. Therefore, the option is D. Option is D. Look at here. D is 0. Option is D. Problem number 9. The output characteristics of a MOSFET are given. VGS 1 and 2 and 3 and 4. Current is 1, 2, 3, 4. The transconductance of MOSFET is how much? 0.75 millis susceptance, 1 millisusceptance, 2 millisusceptance, 10. Because susceptance means conductance and amperes by volt. So take two values, for example, when you say, for example, 2 minus 1 here, 2 minus 1 here, 2 minus 1 by 2 minus 1, change in VGS by change in ID by change in VGS, 2 minus 1 by 2 minus 1, it is approximately 1. But let's see that. 4 minus 3 is 1. You take anything, you have the same. See, 1 to 1, 2 to 2, 3. So change in ID by change in VGS, 4 minus 3, 1. Therefore, option is B. Problem 10. The variation of drain current with gate to source voltage ID VGS characteristics of the MOSFET is shown in figure. Then the MOSFET is what? Once again, the variation of drain current voltage gate to source voltage ID VGS characteristics of a MOSFET is shown in figure. The MOSFET is what? VGS ID. This is the value. Is it N-channel depletion mode, N-channel enhancement mode, P-channel depletion mode, P-channel enhancement mode? By looking at this positive, you can think what type of this. So this is gate EEE 2003 1 mark, because it's not calculation involved, it is only a characteristics to be observed, so it is 1 mark. It has to be a P-channel depletion mode, because N-channel means negative EP comes, P-channel positive EP comes there. Therefore, the option given is C, and then we will be going for device technology to see how op-amps and ICs are manufactured.